proper stars at all, but instead are the stellar mutant power zombies that began their lives in the death of massive stars. As we saw in our previous video on how high-mass stars evolve and die, the cores of these stars eventually become iron. And since iron can't fuse, it cannot produce the energy needed to hold itself up. For a while it hangs in there, but the pressure is so strong it's squeezed into electron degeneracy. But the core keeps gaining mass, and when it reaches 1.4 solar masses, electron degeneracy fails and the core implodes. The core collapses from the size of Mars to the size of Manhattan in just a few milliseconds. But during those few milliseconds, protons and electrons are squeezed into each other to become neutrons and neutrinos. The neutrinos escape, but the neutrons are squeezed together so tightly they exert an even more powerful neutron degeneracy pressure. The collapse comes to a ringing halt at a radius of just a few kilometers. The layers surrounding the core crash down a few milliseconds later and rebound in a titanic supernova explosion. The core is now an exposed neutron star. Because they're both massive and tiny, neutron stars are unimaginably dense. We're talking about something that's between 1.2 and 2.8 times the mass of the Sun, squeezed down to the size of a city. Now, that may seem impossible, but it really isn't. If an atom were enlarged to the size of a football stadium, its entire nucleus would only be the size of a marble, and its electrons would be tiny dust grains whizzing around way up in the upper decks. Now, if that seems like a lot of empty space to you, well, that's because atoms are in fact mostly empty space. But in a neutron star, every bit of that empty space would be filled with neutrons. This is what makes neutron stars so mind-bogglingly dense. A teaspoon of neutronium, the name for neutron star material, would weigh 5.5 trillion kilograms. That's like squeezing Mount Everest into a small lump and dropping it into your teacup. Although it would crash right through the bottom of the teacup, then through the table, then through the floor, then through the earth, all the way through the core, out the other end, and then it would come back and forth through the planet for about 1 billion years, turning the whole earth into Swiss cheese. The insane density of neutron stars creates an equally insane gravitational pull. Typical neutron stars have a surface gravity that's 100 billion times stronger than Earth. But forget even thinking about standing on one of these things to weigh yourself. You'd be instantly flattened into a thin film of quantum goo. In fact, if you dropped a golf ball onto a neutron star surface from a height of just 1 meter, it would hit the ground 0.5 millionth of a second later. In that short time, tidal forces on the star would have shredded the golf ball into a string of atoms. Those atoms would then hit the surface with a substantial fraction of the speed of light, releasing more energy than all of the thermonuclear bombs in the world combined. That extreme gravity gives the star some truly weird and exotic properties. Understanding the conditions inside the neutron star is very difficult because it pushes the limits of our understanding of quantum mechanics and gravity. But even what we do know about neutron stars is pretty mind-flattening. For example, neutron stars are the most perfectly smooth objects in the universe. The tallest mountain on the star's surface is only a few millimeters high. The crust is likely a crystalline lattice structure of iron and maybe some helium nuclei that weren't destroyed when the core imploded. It's effectively a solid crust with a temperature of around 1 million Kelvin. Underneath is a mantle of almost pure degenerate neutrons. The conditions in the core are the least well understood. Inside, pressures are 10 to the 16 times greater than in the core of the Sun. Some models suggest that under these conditions, the neutrons are squeezed so tightly together they cease being neutrons and dissolve into an exotic quark superfluid. But one thing we do know for sure about neutron stars is that they rotate, and they rotate fast. The star was already rotating before it exploded. But as the core collapsed, it spun up much faster, much like a figure skater pulling in her arms to increase her rotation. But when more than a sun's worth of mass shrinks down to just 20 kilometers across, the rotation speeds up by a ridiculous amount. A newly formed neutron star can spin up to 100 times a second. The fast rotation sets up insanely strong magnetic fields. How strong? Well, Earth's magnetic field is somewhere around 30 microtesla. That's 30 millionths of a Tesla. Not the car, the actual unit of magnetism, but hey, if you want to ship me a Tesla, that's okay too. The sun's magnetic field is a lot stronger, around 0.001 Tesla. Sunspots, which are very strong magnetic concentrations on the sun, reach 0.3 Tesla. MRI machines generate fields of around 3 Tesla, and the most powerful magnets inside the Large Hadron Collider reach 8 Tesla. But a typical neutron star generates up to 100 million Tesla. In other words, a neutron star at the moon's distance would erase your credit cards, and it would pay them off as well because all of the hard drives on Earth would also be erased. It'd be the end of civilization as we know it, but you'd be debt-free. The magnetic field lines are so strong they become particle accelerators and launch beams of radiation along their magnetic poles. Typically, these poles are tilted with respect to the star's rotation, turning the star into a cosmic lighthouse. If the beams sweep along our line of sight, we can detect them as repeating pulses of radiation. We call these types of neutron stars pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell, who was then a graduate student at Cambridge. She kept detecting a strange repeating radio signal. After ruling out any problems with the radio telescope she was using, Bell realized that the signal was coming from space. At first, nobody knew what was causing the pulses. The signal was so perfectly timed, they half-jokingly designated the source as LGM-1 for Little Green Men 1. Pulsars lie at the hearts of most supernova remnants. Their magnetic fields churn the surrounding gas like a cosmic egg beater, and their radiation ionizes the surrounding gases. Pulsars are extremely stable rotators, so their pulses act as ultra-precise clocks. In fact, some pulsars are as accurate as atomic clocks. Each pulsar has its own rotation period, so for a while, they thought they could be used to determine your exact location in the galaxy. As a matter of fact, the covers of the golden records affixed to the Voyager 1 and Voyager 2 spacecraft include a pictogram of some known pulsars surrounding Earth. The tick marks indicate the pulsation periods, and the lengths represent the relative distances. The idea was that if an alien species could identify the depicted pulsars, they could reverse engineer Earth's location in the galaxy. At least that was the thinking back in the 1970s. We've since discovered thousands more pulsars throughout the galaxy, and that makes identifying the ones used on the Voyager records a lot more difficult. But we've also learned that pulsars can wobble or precess, and that changes their orientations over time. So some of the pulsars that were once aimed at Earth when the Voyagers were launched aren't aimed at us anymore, at least not as we see them. So we don't think of them as pulsars, we just see them as ordinary neutron stars. Still, it's interesting to think that perhaps with enough information about all the known pulsars, we might one day be able to use them as a kind of galactic positioning system. We could even call it GPS for short. I ought to patent that. A pulsar's rotation is very stable on the timescales of years to centuries, but their magnetic fields drag against the surrounding remains of the supernova, and so they slow down over time. For example, the Crab pulsar is roughly 1,000 years old and rotates about 33 times a second. But the Vela pulsar is about 10,000 years old and it rotates about 11 times a second. Now, left to its own devices, a pulsar should slow down over time, but if the pulsar is in a binary star system, it can actually speed up. As the companion star evolves, it expands into a red giant. If the two stars are close enough together, matter eventually flows toward the pulsar. The pulsar accretes this material and gains mass, but in order to conserve angular momentum, it must speed up in response. These pulsars can spin so fast their rotation periods are measured in milliseconds. The closest millisecond pulsar is PSR J0437-4715. Its name comes from its coordinates on the sky. This pulsar completes one rotation in just 5.75 milliseconds. That's 174 rotations a second. But that is nothing compared to the record holder, PSR J1748-2446 AD, located in the globular cluster Tarzan 5. It's approximately 18,000 light-years from Earth in the constellation Sagittarius and is home to about 30 additional pulsars. But this pulsar clocks in at a ridiculous 1.4 milliseconds. That's 716 rotations a second. That's 43,000 rotations per minute. The pulsar is moving so fast its surface is actually spinning at 15% the speed of light. Now this pulsar is too far away, so its signal is too weak to be directly converted into sound using our current radio telescopes. But it should sound similar to another pulsar, PSR B1937+21, which rotates 10% slower at 642 times a second. That's annoying. The magnetic fields of millisecond pulsars are super powerful, but some neutron stars generate magnetic fields that can be up to 1,000,000 times stronger than a typical neutron star and a quadrillion times stronger than the sun. We call these beasts magnetars. Magnetars are so powerful their magnetic fields actually stretch atoms into long cylinders. At 10 billion teslas, a hydrogen atom becomes a spindle 200 times thinner than its normal diameter. Don't even think about getting anywhere near one of these things. Even if you could somehow survive the onslaught of X-ray radiation from the magnetar, its magnetic field would rip you apart at 1,000 kilometers. Oh yeah, and that stuff about a neutron star erasing the hard drives on Earth from the moon's distance? Well, a magnetar could do the same job from Pluto. Magnetars are thought to be rare. Only 1 in 10 supernovae ever produce them, and they probably don't last very long either. It's thought that their magnetic fields drag on the surrounding interstellar medium so hard the star would slow to normal pulsar speeds after just a few years. But while they're still active, they are the most powerful magnets in the universe, and when things go wrong in a pulsar, all hell literally breaks loose. When our sun becomes active, magnetic field lines connect and short out, unleashing the equivalent of 1,000,000 hydrogen bombs worth of energy in just a few minutes. But magnetars are on a whole other level. Their magnetic fields are bound to their spinning crusts, so a change in one automatically results in a change in the other. Magnetars rotate at a significant fraction of the speed of light, and the crust is fighting ultra-strong centrifugal forces. That puts the crust under incredible stress until it finally adjusts itself to alter its shape. That adjustment creates a tiny crack in less than a millionth of a second. Even though the crack is less than a micron in size, a titanic amount of energy is released. The event is called a starquake, and it's one of the most violent episodes this side of a supernova. The largest starquake ever recorded was on December 27, 2004. It came from the magnetar SGR 1860-20. The energy released in the starquake would have been equivalent to a magnitude 32 quake here on Earth. The quake occurred 50,000 light-years from Earth, yet it compressed Earth's magnetosphere and partially ionized its atmosphere. By the way, 50,000 light-years? That is halfway across the galaxy, man, and yet it had the same effect on Earth as a typical solar flare. If that starquake were at 10 light-years, it would have triggered a mass extinction. Luckily, we don't need to worry about death by magnetar. We only know of about 30 of them, and there's probably only 3 or 4 dozen in the entire galaxy. And starquakes are even more rare. We've only detected a handful of them in the last 40 years or so. We've learned a lot about neutron stars in the last 50+ years, but they're still continuing to surprise us. In December 2019, 2 independent teams of astronomers made the first ever map of a neutron star. Although their results were similar, neither showed the magnetic poles emerging from the northern and southern hemispheres of the neutron star. Instead, both magnetic poles were mapped to emerge from the star's southern hemisphere. Does this mean our understanding of neutron stars is fundamentally wrong, or is it merely incomplete? We'll investigate that in a future video. But before we get to the next video, let's talk about the last one about what's happening with Betelgeuse. Many of you pointed out that Betelgeuse may have already supernovaed, but because it's so far away, its light hasn't reached us yet. Others noted that the unusual dimming we're witnessing now actually happened about 640 years ago. Both statements are absolutely correct. But since light travels at a finite speed, we have no way of knowing what the star was doing until its light gets here anyway. If Betelgeuse is 640 light-years away, we are by definition seeing it as it appeared 640 years ago. Now, I suppose I should have pointed this out in the video, but then I'd have to point that out for everything. Light takes about 1 second to get from the moon to Earth, so we only see the moon as it appeared 1 second ago. Likewise, we always see the sun as it appeared 8 minutes ago. Even this video is what it looked like a couple of nanoseconds ago because it took light that much time to go from the screen to your eyes. We're always seeing into the past thanks to the speed of light, and that leaves us with a relative concept of now. I also got a fair amount of comments about my pronunciation of the name Betelgeuse. I call it Betelgeuse, but some said it should be pronounced Beetlejuice, and others were careful to note that it was in fact a translation, or maybe a bad translation from the original Arabic. However it may be, the pronunciations range from Beetlejuice to Betelgeuse to Betelgeuse to Betelgeuse to Betelgeuse. I just split the difference somewhere and call it Betelgeuse, although I'm probably pronouncing that wrong as well. Maybe I should just start pronouncing it as Alpha Orionis instead and just be done with it. Or is it Alpha Orionis, or is it Alpha Orionis, or Alpha Oriona? Oh man, the comments are coming. Many thanks to my Patreon supporters who are helping to keep this channel going, and I'd like to welcome my newest patron, Glenn, and give another shout out to my cosmological sponsor, Stephen J. Morgan. If you'd like to help support this channel for the price of a cup of coffee, head on over to my Patreon page. And if you'd like to see what's up with Betelgeuse and how massive stars evolve and die, I've got some videos on them both that we can check out once we're done here. Until next time, stay curious, my friends.